Good morning, everybody. It's my pleasure to welcome you all to ICTS. I'm Rama Govindarajan. Today I'm standing in for our director, Rajesh Gopakumar, who's not in town. So it's customary that he gives this presentation. So this was an aerial view of ICTS some years ago, and here's what it looks like now. So it changed a lot in greenery, and it's kind of representative of how ICTS is growing in the past few years. So we're in an exciting phase of growth right now. This is a picture of our library, which was painted by one of our actual program visitors. So if any of you is interested in artwork, we can display that next time if you send us something. This is one more example of artwork and of our blackboards. So ICTS has basically three mandates. It's in-house research, programs such as this one, and a variety of others, and outreach. So these three are equally important to us, and they go hand in hand. And we are one of the newest centers of TIFR. This center was like patterned on other centers in the world, such as KITP in Santa Barbara and the IIS in Princeton. But there's like a lot of differences between how we do it and how they do it. We have our unique mandate, which is like, to intertwine these three things together. And these are the primary subjects we are interested in. This is a picture of our faculty as of now. You can see we are growing. And these are basically the areas in which in-house research happens. We don't have departments, so we have like this very loose groupings, but there's a lot of crosstalk of people collaborating with each other. And this is the number that is there right now. Maybe the PhD number is a little higher than what's reflected here. We're also like pretty international in our partnerships apart from the programs. And here is an example of the number of things we have in terms of formal collaborations across the world. And of course, there's many, many more individual collaborations of faculty with people in different universities all across the world. So programs like this one, this is just an example of very small sample of the programs that we've held in the past. And you can see that they're very detailed and very diverse as well. So the nice thing is that the global scientific community can actually like propose programs over here. So if any of you has a thought for a program, then like we have calls twice a year. One just got finished, but one is coming up in December, and you can submit a proposal. Actually, the committee will work with you to improve the proposal, and lot of polishing of this will happen with the committee. And these are typically 2 to 3 weeks long, although this one is shorter, I see. And we have like discussion meetings like this one as well. And our emphasis is on a pedagogical component for young researchers. So like you can see the numbers, they're very, very large. 30 to 40 programs every year with so many external participants. And so we are hoping that we will become a bigger and bigger influence in the country's research and serve as a science hub where people can come and talk about research. So that's how we distinguish, programs from the standard conferences. That's very important for us. And this, the number of talks that have been held have resulted in this very amazing repository, which is continuously growing. And we've got already 6.5 million views, which is pretty good. So almost any topic that we've covered that you'd like to hear a lecture on is available online. So like this is a sample of the kind of programs we've conducted. You can see the diversity, and all of these have resulted in further research. So it's my request to you that in your program, if you're coming up with new projects, new questions, and you're handling them together, so please do acknowledge ICTS in your papers, and we'd always be happy to get a mail to know about, how this program of this week has benefited you later on. And yeah, we have, apart from programs, we have many schools, and you can see again the large variety and how frequently they happen. For example, this summer school for women in physics and maths, both of them, they've been held annually. There's a summer school for women in physics, which is not listed here. So these are held annually, and there's like many examples of schools. Some of them are in collaboration with other places. So apart from programs, we have special lectures which have names, and each of them, for example, the D.D. Kosambi lecture is on humanities subjects, humanities and social science subjects. So we have like speakers from those. And outreach, it's our third mandate, and it's as big as everything else. And here we are really punching above our weight class. So we have a huge variety of activities going on, some of which are represented here. And in science pedagogy, there's a math circle network, which is going very well. It's for school children. And Copy with Curiosity is a program that's gaining a lot of attention. And that's basically what I wanted to tell you. So please have a great week and a great program. Thank you.
Okay. Let me just introduce myself. My name is Jürg Kramer from Berlin. I'm one of the organizers next to Anilatmaja, who is here, and Baskar, who is upstairs also among us. And finally is also Anna Pippich from Konstanz. She is also one of the organizers. Unfortunately, she cannot only participate remotely, so to say. So let me welcome all of you. We are very thankful that you are here. And let me in particular thank the speakers, the lecturers of this week, that they have agreed to be with us. Let me also thank ICTS for hosting us for this at this nice place for this workshop. And with the Royalty organization, I do not have to say more things at this point in time. There will be announcement made. One indication is that the program on Wednesday will slightly change, but we will announce that in time. So I don't want to steal the time of Raghuram, so let me just switch to the first talk of a series of four talks. So Raghuram from Fordham University in New York City will introduce us to Eisenstein, cohomology, and congruences. Thank you, Raghuram, that you're being with us.
Okay. Hello, good morning. I thank the organizers. Where's Baskar? Baskar, Anil, Kramer, vielen Dank for the Einladung. Did I get that right? And to Anna von Pippich, who we just heard isn't here. Thanks for giving me this opportunity to give an exposition of certain topics which are somewhat dear to me. Yeah. This is about Eisenstein cohomology and congruences. I'm going to structure this course. It's really two topics that I want to talk about. The first part of this is going to be a topic which has gained a lot of popularity. It's been around since the 80s, but somehow has had a renewal of interest. This is about denominators of Eisenstein classes. And I'll introduce this with really the most elementary example that one can work with, Eisenstein series for SL to Z. This itself, the first two lectures are going to be about this topic. In lecture 1, I'm going to talk about a theorem of Hida back from the 80s, which is for, I just say right now, just for SL to Z. And in lecture 2, I will add a tiny amount of ramification and talk about Christian Kaiser's thesis. This is when I have a level P structure. And in going from 1 to 2, I'll be reorganizing my thoughts. And this second lecture is going to give me a springboard to talk more generally about congruences. And in congruences, before I can really get to congruences in the third lecture, I'm going to talk about a general framework for studying Eisenstein cohomology. And in the fourth, this general framework, maybe I'll talk at the level of GLN. I'm going to keep my base field to be Q, rational numbers throughout the entire course, just so that I don't have to get into a whole lot of bookkeeping for a general number field. But you can talk about this at the level of a reductive group or a number field if one wanted. But I'm going to work with GLN. And in the fourth lecture, this is going to be how one can use Eisenstein cohomology to prove congruences for special values of Rankin-Selberg functions. Classical Rankin-Selberg function, so GL2 cross GL2. So this is the general framework. This first part, denominators, I've been looking at this with joint work with Xiao Yu. It also goes by Vivian Yu. He's a graduate student at Columbia. And this part, this is really Narayanan's thesis. Narayanan is sitting somewhere here. And this general framework, I'm going to borrow heavily from my book with Hida. This is the framework of my 4 lectures. Okay. All right, going back to, I seem to recall from my previous visit to ICTS, one shouldn't write too close to the top, right? I don't know, there's somewhere there was some problem. Okay. You guys can see what I'm writing way in the back. Okay. So I'm going to give myself an integer k, an even integer, and maybe at least 4. And I want to look at this weight k Eisenstein series for SL to Z. In this entire talk today, gamma is going to be SL to Z. There are 3 normalizations for defining your weight k Eisenstein series, and all 3 have their virtues, and you have to take your pick depending upon what you want to do. So there is I borrowed this part of my presentation from this beautiful chapter of Zagier's chapter in this book, 1, 2, 3 of modular forms. It's an amazing chapter. Every time I go there, I learn something new. It's just got a wealth of information. Anyway, so there is I'm using Zagier's notation. There's an EK, there's a GK, and then there is a bold-faced GK. And all 3 have their virtues. So what's EK? EK has the virtue that it's normalized by asking its first Fourier coefficient to be 1. And it turns out that all the other Fourier coefficients are rationals. GK, whatever it is, I'll give you the definitions in a second. This has the virtue that it's easy to compute the Fourier coefficients. And this bold GK has the virtue that almost all Fourier coefficients are integral. A0 could be rational. Okay. And what are the definitions? So EK I want an Eisenstein series. I want a modular form for gamma. The easiest thing you can do is just average over gamma. Just average the constant function slashed by elements of gamma. But then if you did this, there's an extra counting. You go modulo, you sum over gamma mod gamma infinity. That gamma infinity is that. Yeah, maybe plus minus. And then if you work this out, this turns out to be the sum over integers C and D, integers C and D, with C and D being relatively prime of 1 over CZ plus D to the K. Instead of doing this GK is a similar looking thing where you sum over all integers M and N, not both 0, of the same thing, 1 over MZ plus N. And then you break the summation using its the greatest common divisor of M and N. Let D be the greatest common divisor of M and N, and you sum over D, and then you sum over elements which are relatively prime, and then it's relatively trivial to see that this is zeta K times EK. And this GK as well, you see the zeta K, and you use some basic theorem about rationality of zeta K, and I want to kill it by multiplying by K minus 1 factorial by 2 pi I to the K of GK. So these are the 3 normalizations. And I'm going to show you the Fourier coefficients in a second. And of course, all of them are scalar multiples of each other. And they're all weight K modular forms for S into Z. So what's the shape of the Fourier expansion? Fact, theorem. This is all classical, I'm kind of just warming up really, and warming all of you up into deeper waters. So the shape of the expansion is this bold GK. That's what I really want to look at. This is minus BK by 2K plus the sum n going from 1 to infinity of sigma K minus 1 and Q to them. Q always is e to the 2 pi I Z. And if I want to get that normalization, then EK is going to be, well, you just divide by this, start with 1, and its reciprocal sits there, and then you realize that that is also 2 over zeta 1 minus K sum n going from 1 to infinity. Sigma K minus 1 is the sum of the K minus 1's powers of the divisors of n, Q to them. I'm using some facts about the Riemann zeta function. The easiest way to remember the rationality result, if K is even, I said K is even, right? K is even. Then zeta K on the right is, some up to some rational pi to the K, or I could say up to 2 pi I to the K times some rational. There's some explicit form for the rational number, or it's easy to remember what's happening on the left. Zeta 1 minus K is minus BK by K. This BK is the kth Bernoulli number, and I'll show you a definition of Bernoulli in a second. So far, so good. You got to, please feel free to stop and ask me if anything is unclear. Keep this in mind. This little term sitting here is the heart of the story of today's lecture in some sense. There's a zeta 1 minus K sitting down there. All right, if you haven't seen this, how does one get these kind of Fourier expansions? I will just tell you just a hint of a proof really is you want to work with this guy. This is the one easiest to compute Fourier coefficients with. And you just have to get started on the right footing and then follow your nose. The right footing is this is an identity due to Euler, that if I look at, how does it go? Summation 1 over z plus n, running over all integers. Z is some complex variable as long as it's not an integer itself. Then this is pi over tangent pi by pi z. You start with this, and then you follow your nose. You write tangent as sine over cosine. So this looks like pi cosine pi z by sine pi z. And then you stick in the definitions in terms of e to the something. So there's a pi, there's a e to the I pi z plus e to the I minus pi z divided by e to the I pi z minus e to the minus I pi z. I don't know, maybe there's an I sitting somewhere. Sine of this, I should look into my notes instead of doing this real time. Yeah, so there's an I pi. And then you multiply by an extra factor of e to the I pi z, and this now looks like minus I pi 1 plus q over 1 minus q, something like this. Expand this through a power series expansion. You get a certain expression, differentiate that expression, and now you differentiate this k times. Why does this do the job? You look at this, well, there's a term for m equals 0. Well, there are terms for m equals 0. That just gives you zeta k. And then for m not equal to 0, if I fix that m not equal to 0, this would be exactly what you would get by differentiating k times and sticking in mz instead of z. And then you follow your nose. And then if you clean it up, you get this, using this rationality result for the Riemann zeta value. I don't really know, this is just, again, in some sense, I'm still warming up. This proof of the Fourier expansion is not really needed for me. This is considered to be standard fact. All right, so what are these Bernoulli numbers? In some sense, I'm going into my second section. I want to talk about, well, this course is about Eisenstein, cohomology, and congruences. Any discussion of congruences is going to start here. Ramanujan's 691 congruence. So I want to show you what that looks like, and that's going to play a role keeping this in mind. And then when I map everything into cohomology, which I'll do maybe 15 minutes from now. All right, so what is Ramanujan's 691 congruence? So towards that, let me just recall Bernoulli numbers. This is given by a certain power series, t by e to the t minus 1. Some people would write t e to the t by e to the t minus 1. That only changes the first term. 0 to infinity, bn t to the n by n factorial. There's a definition of Bernoulli numbers. And then you can compute Bernoulli numbers to your heart's content. And you B2 then is 1 over 6. B4 is minus 1 by 30, and so on. And let's look at B12. B12, the 12th Bernoulli number is minus 691 divided by 2730. Okay. And this 2730 is also minus 691. If you look at the prime factorization, 2 into 3 into 5 into 7 into 13. In any case, small primes. The point is, in these kind of numbers, anytime you see a prime sticking out, you'll always have a supply of small primes. Anytime you see a prime sticking out, that prime is something of interest. This is a sort of rule of thumb. That prime will be like a congruence prime somewhere. And this 691 is the same as that 691. So let's look at G12, so for example, if I look at the weight 12 Eisenstein series, which has all the Fourier coefficients starting from the first one to be integral, then minus B12, this divided by 24, so that becomes 691 divided by 24 times 2730, which happens to be 65520, plus the sum n going from 1 to infinity of sigma 11 and q to the n. All right, and what is this number in the denominator? It's in all the small primes times 24, okay, all just small primes. You don't see any 691 there. So if I read this mod 691, G12 looks like a cusp form. Modulo 691. And Ramanujan's congruence makes this precise. What Ramanujan proved or showed is that I have to, first of all, what is Ramanujan's delta function? You look at delta z is by definition q times the product n going from 1 to infinity at 1 minus q to the n for the 24. And then this, you expand this coming 1 to infinity of, we just call the coefficients tau of n. And what Ramanujan proved was the congruence is tau p is congruent to p to the 11 plus 1 modulo 691. This can also be said as this guy, G12, rephrased Ramanujan's congruences that the G12 mod 691, this term goes, so I'm really looking at sigma 11 n modulo 691, and that turns out to be tau of n modulo 691. G12 is congruent to delta modulo 6. Let me show you a quick proof of this. It's kind of cool. Proof, again, in the spirit that I just show you the basic steps in the proof, and then it's an exercise to fill in the details. It hinges on the fact that, well, I didn't say where this delta lives. This delta is literally the very first example of a cusp form you come across. This is a weight 12 cusp form for SL2Z. Actually, more so, and that's the crucial point, this entire space of weight 12 cusp forms for SL2Z is spanned by this delta. So this is a one-dimensional space, and delta is the cusp form. Because this is tau of 1 is just 1. It's normalized. So it hinges on this fact, and what you do, you got a supply of these Eisenstein series, and you play around, and you look at E4. Let's look at E4Z for a second. E4 would start from 1 plus 2 over zeta 1 minus k. Zeta 1 minus 4 would be minus B4 by 4. Thought I wrote B4 somewhere here. And then you will see that this is 1 plus 240 times the sum n going from 1 to infinity of sigma 3n. That's E4. Let's look at E12. E12 would be 1 plus, I'm going to invert this number and stick it in there, 65520 by 691 times a certain sum, sigma 11 and q to the n. Then you look at E4 cubed minus E12. Then this one cubed will cancel out with that one. And you look at the term for Q, sigma, anything, for n equals 1, these are all 1s. So I have 240. And then when I'm cubing this, it becomes 3 times 240. So that's 720. Minus this guy, 65520 by 691. This is the constant multiplying this times Q plus some other terms. So if I pull this out, then the coefficient of Q becomes 1. This is a cusp form. You know, I've killed the constant term. So this is a cusp form. It's this multiple then of delta, because it lives here in this space, and that space is one dimensional. So you take this equation, and then you basically stare at it long enough, and you realize that this implies the congruence, because take this, multiply this equation by 691, observe that E4 has all integral Fourier coefficients. So after multiplying by 691, when if I read it modulo 691, so multiply by 691 and then read modulo 691, this disappears by what I just said. All coefficients are integral, multiply by 691 and mod 691, that's gone. Minus 691 times E12. So this 691 cancels out. And so I'll get minus 65520 times this sum. Is equal to or congruent to 691 times 720 is gone, minus 65520 times delta. And this is relatively prime. 691 doesn't touch this. Beautiful. It hinges on the idea that the space of cusp forms of weight 12 for SL2Z is one dimensional, and integrality of all the Fourier coefficients of E4. And okay. Yeah, sure. No, because this guy is, pretend this is an integer, but this is a rational number. It's like this rational number. So 691 times this rational number simply becomes 65520. So yeah. This has seemingly more information, but then both are eigenforms, and if I know this and know some kind of multiplicativity, you can kind of piece them together, and you will get tau of n is congruent to n to the 11 plus 1 for every integer n, not just for primes. I might have added. Then it's literally the same. What did I write? Thank you. So, if n is prime, sigma 11 of p is p to the 11 plus 1. Otherwise, I have to write sigma 11. That's an 11. Any other questions? If you haven't seen this, you know, I don't know, it's deeply satisfying if you like modular forms. Okay, and what I want to make a case for is one sees this, maybe I should, let me go elsewhere. A remark. We are going to see this prime, 691 is a prime, by the way. 691 can be seen as a denominator of an Eisenstein class in H1 of SL2Z with coefficients in an 11-dimensional module. Okay. So this is where I'm headed. Okay. So I got to introduce this aspect of modular forms, and that is really afforded by the Eichler-Shimura isomorphism. So here's a quick introduction to Eichler-Shimura. This is Harder's theorem, by the way. I mean, I'll be stating this theorem more precisely. This goes back to 80s. So what's the Eichler-Shimura isomorphism? You have to go back at some point of time in your life and look at Shimura's book. Shimura's chapter 8, is it? Where this is, you know, all the basic details of what goes into the isomorphism is written there. I'm going to write this in this form. So the theorem is, there is a Hecker equivariant isomorphism from the space of cusp forms of some weight for gamma. In this talk, gamma has SL to Z, but this works more generally. So I'm going to organize my thought slightly differently. Space of modular forms of weight k plus the space of cusp forms conjugated to H1 of gamma with coefficients in a module, which I'm going to write V sub k minus 1 C dual. Okay. I'm going to explain all these notations, what we mean by. So mk gamma, I've already used this. This is just the space of weight k modular forms for gamma. Sk gamma is the space of subspace of cusp forms. A0 is 0. And Sk bar is just for every cusp form, you just take its complex conjugate. So those are the ingredients on the left. What are the ingredients on the right? Vk minus 1. So Vk minus 1 without any qualification of, here I put a comma C, and this is going to play a critical role as we go along. So right now, Vk minus 1 is by definition the k minus second symmetric of Z2, two copies of integers. SL2Z naturally acts on Z2 by matrix multiplication, and so by functoriality it will act on any multilinear construction, symmetry part construction, or more concretely, this can be realized as the space of polynomials in two variables, which are homogeneous of degree k minus 2. Symmetric pass. So you take some tensor algebra and then you go. Okay. So yeah, I don't really need this. Let's take this. I guess in this, the sub of tensor would make this to be on the nose. Yeah, I'm going to get to the dual. And so, what is the action of SL to Z on this? If I take a gamma and a polynomial, gamma p is another polynomial, you just hit these variables. Think of this as a 1/2 matrix, and so I hit it on the right, something like this. And so once I have this, I can, and this is working algebraically over integers, and so I can base change to any ring, any field. I would get a representation of, if I take F, any field, I would get a representation from SL to F to GL of Vk minus 1 F, where by this I mean I just tensor it up with F. So that's what I mean by sticking in the C. It's a complex vector space here on which SL to C acts, and really I only want SL to Z acting on that. And furthermore, yeah, what's the dual? Vk minus 1 check is going to be the Z dual of Vk minus 1. And then I can base change that to whatever field I want. Okay, so, and what is the shape? So these are the ingredients going into the right, and given any gamma module, I can look at its group cohomology. This is just group cohomology. And what is the shape of this isomorphism? It's very explicit, but very transcendental. And that's what makes the questions delicate and interesting. So if I call this isomorphism something, I'm going to call it R. If I take a modular form of some weight, take an element here, I want to tell you what is R of F. So that should be something H1. So I need to write down one cocycle for gamma with coefficients in this module. So that's really a function, cross homomorphism. So it will take it as an input, an element of gamma, and produce something in this module. What's an element in this module? It's a kind of linear functional. So I need and some vector here, and then I have to give you a scalar for all those ingredients. So given an F, and given a gamma and gamma, and given a P in Vk minus 1, R of F on gamma, this is my one cocycle with values in Vk minus 1 check. So its value on an element in Vk minus 1 is, you write down some period integral. So it's an integral tau to gamma tau of F of Z, P of Z1, something like that. I hope I got that right. And you can do a similar thing sticking in some bars over here. But I really want to start from modular forms. And now I introduce this Eisenstein series of some weight. This Ek is sitting in Mk. Ek is sitting here. Well, follow it up by the Eichler-Schummer isomorphism, and I get some class in H1. So here's the definition of my Eisenstein cohomology class. I'm going to denote this omega ice K to be the image under the Eichler-Schummer isomorphism of Ek. This Ek is this Ek, normalized with the first Fourier coefficient to be 1. Okay. Where does this live? It lives here. So you have to keep this in mind, that my Eisenstein class is a priori in H1 gamma Vk minus 1 C check. And this Eichler-Schummer isomorphism is a transcendentally defined isomorphism. On the face of it, there's no rationality, there's no rational issue here. I'm working with complex numbers. So far, so good. Any questions about Eisenstein? Yeah. What is P? P is a polynomial in 2 variables. So, I just evaluate this at, for X, I put a complex, something in the, I didn't say where Z lives, everything is in the upper half plane. So this becomes a complex number. F of Z, that's a modular form. It's a function on the upper half plane, a holomorphic function on the upper half plane, taking values in complex numbers. These are all complex numbers. And this integral, I didn't say what tau is. So tau is really some element in the upper half plane. And one has to sit down and check that there is a tau independence in this definition of this integral. That needs to be said. And R is independent. Now, integral makes sense? Yes. Any other questions? Yeah. These are all things to check. It's not, this is just this recipe you don't see that. So you have to sit down and check. If I had R of F of gamma 1, gamma 2, this becomes gamma 1, gamma 2, and to integrate from tau to gamma 1, gamma 2, you integrate from tau to gamma 2 tau, and then from gamma 2 tau, you go to gamma 1 of gamma 2 tau and sit down and check what you have to check. Any other questions? Yeah. Shimura's chapter 8 has every possible detail you care about. You have to go there. Shimura, Introduction to the Arithmetic Theory of Automorphic Functions. It's the Bible of the subject, if you will. Yeah. Here, F is any field. It can be any ring, really. I really need this only for Q and for complex numbers. It's any field. Yeah, sorry. I know I'm kind of zipping through because I want to get to the heart of the matter, but on the other hand, there's no point going fast if please just ask me anytime. You don't have to wait till I ask you to ask me questions. Feel free to interrupt. What does that representation do? If I work with weight K modular forms, it turns out that I need to be working with a particular coefficient here, coefficient system. For weight 2 modular forms, if K is equal to 2, then this is like the trivial representation. So constant coefficients, you look at cohomology with constant coefficients. For higher weight modular forms, in cohomology, you have to carry this coefficient system. This is one way to say this. There's a representation theoretic way to say this, that if you have a discrete series representation, I'm not talking so much in the automorphic language, automorphic representation theoretic language as yet, but if I did a discrete series representation has cohomology with respect to a certain module, and that module there's a rigidity due to Wigner's lemma that these two should have the same infinitesimal characters. And that kind of forces you to look at this and this only. You don't have a choice in the matter. This is the unique K-1 dimensional representation of the algebraic group SL2. Yeah. No, that's an entire subsection in Shimura. You have to sit down and check that. Yeah. So I haven't even showed you the shape of Hecke action here. One has to go through, how do Hecke operators act here, how do they act there, and you have to do something. I'm just asserting there is this isomorphism, and we take this as a black. Yeah. That's answer. So there are Hecke operators acting on everything in sight, and there's a theory of Hecke operators and how they act. So I won't be going into that here. It just takes up too much time. If you have seen some modular forms, you would have seen some Hecke action, and a similar thing you do on the cohomology side. It might be easier to show this when I work adelytically in my second lecture. Okay, so we are here now. I start with this weight K Eisenstein series. I apply the Eichler-Shimura isomorphism and lay my hands on a particular cohomology class. What can we do with this cohomology class? So what I want to do is I want to talk about denominator of this class, omega K Is. But what would one mean by that? Pretend that this is just complex numbers. Pretend this was one dimensional. What does it mean to talk about the denominator of a complex number? That doesn't really make sense. It would make sense if this were a rational number. If I had a rational number, then, well, there is some denominator. If I write it in some reduced form, there is a... So to talk about denominators, I need to talk about rationality aspects of this Eisenstein class. So towards that, rationality and integrality. I'll just say cohomology, I'm only working with this H1. So first of all, I'm going to just transfer my cohomology group into a different cohomology theory. I'm going to relate group cohomology, which I've been working so far with, and transfer my attention to sheaf cohomology. So far I've been writing H1 gamma with coefficients in some module, I'll just say V over C. And this is isomorphic to H1 of this space H mod gamma. H is my upper half plane, which I thought I wrote somewhere. I said it. H is the set of all. And I look at this topological space, and this module, this gamma module, gives me a sheaf. And to denote the sheaf, I'll just put a little tilde on top. And here's a very quick recipe to lay your hands on the sheaf. I got this upper half plane, and you just take the set theoretic product of this with this vector space. And I can project to the first factor. There is a gamma action on H by linear fractional transformations. There's a gamma action on V. V is a gamma module. So there is a diagonal gamma action on this product. So there's a diagonal gamma action. To denote the diagonal action, I'll stick in a little delta. And then if I go, this projection to the first factor will induce a map from this object to H mod gamma. So this is some kind of vector bundle on H mod gamma. And then I can look at sections of this. Or a more kind of concrete, what is a sheaf? For every open set, I want to tell you what are the sections of that open set. So here is H mod gamma. And you look at H projecting to H mod gamma. Take an open set here, and I want to show you what are the sections over this open set. So take an open set. Let me call this map something, say pi. I pull back this open set. So pi inverse u lives here, which is open by definition. And pi inverse u, so sections over u for this sheaf would be functions from this pi inverse u to the representation space, which is gamma equivariant. So S of gamma z would be gamma on S of z. This gamma z is linear fractional transformations, and gamma on S of z is via the representation of gamma on V. And then you have to check it's a sheaf, and then somehow you stare at the complex which realizes group cohomology, and you stare at the complex realizing that sheaf cohomology, and then somehow you realize that they are really computing the same thing. I'm going to start working with this. And the shape of this rationality that I'm talking about is, well, this class omega ice k lives in H1 of H mod gamma with coefficients in this Vk minus 1 check over C. By definition, it came as under the image of the Eichler-Shimura of this classical weight k of Ek. So it lives there. But this guy has, this gamma is, is SL to Z. It also acts on the Q structure of this representation. So it acts on this. So this is a complex vector space. This is a Q vector space and is a Q structure. So this is my rational structure. I can attempt to do something even better. After all, this Vk minus 1, I started with polynomials with integer coefficients. So I got Vk minus 1 check. If without any qualification means over integers, I can look at H1. The integral module sits inside this rational vector space. This inclusion induces a map in cohomology, but this need not be an inclusion, because this guy is in general, this is some finitely generated abelian group. It could have some torsion. So if I take the image of this in the rational structure, then I'm going to put a little bar, and then I can talk about this inclusion. So let me put this down. H bar 1 is the image of H1 maybe some dualize. So take the image of integral cohomology in rational cohomology, and that provides an integral structure on that rational vector space. It's in effect, it's the same as this guy modulo torsion. My class lives there. Theorem, it actually lives here. So first I have to prove that. This is a class which came out of a transcendental construction. It lives in a complex vector space. Theorem is a rational class. Once it's a rational class, I can ask about its denominators. And this denominator is going to be my 691 if my k is equal to 12. So that's the beauty of this theorem. So let me state, oh my God. Let me at least state the theorems. I don't know what was the section. So the main theorems. First is rationality. So here I'm asserting that this Eisenstein class, which a priori came out of a transcendental construction, in fact lives in this rational structure. It's a rational class. Once it's a rational class, you can ask for its denominator. So what does one mean by that? If I had a rational number, I can talk about a denominator, and we pretty much do the same thing. Definition. I can look at this ideal, which I'll call D of omega i's k is the set of all integers, so that this class multiplied by this integer becomes an integral class. So I look at all possible denominators that what do I need to kill so that because this rational class becomes and maps down, this rational class lives there. Look at all integers, that integer multiple of that lives there. Or I can look at the PID, I can look at this generator. So I can look at define the denominator as delta i's k is the infimum of all of this, the minimum of all those non-negative integers, so that, well, think this is a generator of this. So this is my denominator, definition of a denominator. And so the next theorem, the main theorem, really is this is a theorem of Hida, going back to the 80s. He had some sketch of a proof, and then his book on cohomology of arithmetic groups kept evolving over decades. That book has just arrived. He finished that book just before he passed away. So that has details of this proof, but there's a beautiful paper by Becky and Sakamoto, which just appeared in Essential Number Theory in 2025. It's a long paper where it takes almost 40 pages to write down a proof of this theorem, that the denominator of this Eisenstein class is the numerator of zeta 1 minus k. And so as an example, if I look at the denominator of this Eisenstein class in weight 12, you'll see the number 691. And this then becomes an exercise then to, from here, show Ramanujan's congruence follows. Okay, I've kind of run out of time. So what I want to do, I know I started a little, yeah. I can take a few more minutes. Yeah. Thank you. As I was saying, so Harder had a sketch of the proof, and there's a paper of Harder and Pink, also in the 80s, where this theorem is mentioned, and Harder's book kept evolving over time. And these guys wrote down all the details that you need. It's a very nicely written paper. I recommend you to go and look at this. There are versions of this theorem in various other situations, and what you and I are doing are trying to just understand this in totality. So what is involved in these two steps? I got this cohomology class, which is here, and I want to make it rational, and then I want to study its integrality properties. So there are two steps. So let me just give you what goes into proving rationality. So what goes into proving rationality is the idea that Poincare duality works rationally, plus a whole lot of other things. So proof of rationality, the essence is this. My class lives, this omega i's k, this lives in H1 with coefficients in some module. This H upper 1 pairs with H lower 1 with coefficients in the dual module to C. So this is Poincare. Well, all these homology and cohomology groups have their rational structures. Okay. I want to push this guy here. What you do is you show that paired with everything in the rational homology gives you a rational number. That will force this to live here. So what one needs to prove is verify that the pairing of this Eisenstein class with rational homology, there's a bunch of numbers, all these numbers are rational. So this is what we need to check. So at that time in the 90s, I mentioned Christian Kaiser, and Harder had a bunch of other students. So one of the other students wrote down, explicit generators. Writing down some generators is not so hard, but proving that they exhaust all of homology needs some work. And then for those cycles, one has to compute some explicit. I'll just put that and then I'll stop. One shows through a computation, and this is serious, that paired with a certain class that you're going to cook up, which depends, tau is always some variable in the upper half plane, so some class which one has to construct, and then one shows these classes generate the rational homology, and the pairing involves a bunch of zeta values. There's no way I can remember this. What is nu? Nu is an integer between 1 and, it's a bit of a pain to keep track of all the normalizations. I think it's k minus 3. So k better be at least 4. Zeta minus nu, zeta nu minus k plus 2. Zeta is all Riemann zeta function. Zeta 1 minus k minus zeta minus nu minus zeta nu minus k plus 2. So there is a certain calculation of this shape. This is of course meaningless because I haven't showed you what really is my construction of the cycle. So there is a cycle to be constructed in rational homology. You have to convince yourself that these cycles exhaust all of this rational homology. Then this class, my Eisenstein class, paired against these cycles, spits out some combination of zeta values. All these zeta values you see, everything on the right-hand side are all on the negative side. They're all rationals. And you also see this guy, zeta 1 minus k, sitting there, which is your hint that the denominator of this class is this guy. And I mentioned this fact that zeta, zeta 1 minus m is minus bm by m. This is always rational. If m is even, this is rational. If m is odd, it's 0. So this is the calculation. This calculation runs into some 20 or 30 pages in Becky-Sakamoto. It's not trivial. You have to do this one prime at a time. You've got to use Kubota-Leopold functions. There's some serious work to do. And then you descend down to rationals again. So I'll try to give you a feel for this next time, and which will also give you some idea of why it's believable that you see this zeta here. It's for the same reason in the EK, I told you to remember there was a zeta 1 minus k sitting in the denominator. It's the same zeta 1 minus k. And so, you can see 691 as a denominator of an Eisenstein class. This is a different interpretation of Ramanujan's congruence. That's the beauty of this whole calculation. Okay, so thank you, and I will continue with this in my second lecture.
Well, thank you for the very nice first lecture. Are there some further questions? Let's take one or two, if there are.
Say it again. So it's relatively easy. So this, you have to think in terms of modular symbols, and it's a path from minus 1 by tau to tau. Tensor, this nu is really one of the generators of this. For every vector here, I take a generator. So it has this shape. But this simple-minded recipe doesn't quite give you a homology class. Then this has got to get massaged in some way. You have to do some p modification, to make it live here. It doesn't quite live here. You go to some ZP or QP, you work there, and then you come back. So you have to work this theorem of Harder's. Denominator is the numerator. You verify one prime at a time. And for that prime, you map it to 1 over tau. There's some tau, and then this tau, there's a tau here, but ultimately this tau is irrelevant. There's a tau independence. So the easy answer to your question is it's easy to start with, but then it's not simple. You have to do something to push it into this homology.
Okay, if there are no further questions, I mean, you will be around, so one can ask you during breaks and free time. So I think we stop here. Maybe we take 5 minutes after 11 so that the break is almost half an hour. So we resume by 11:05 with Jacques Dilouin's first talk. And now let's have the break. And this is outside, and thank Raghuram once again for the nice talk.